Hey Miss B, my name is Steven Matthew, and today I'm going to be presenting my Chemistry A to Z final project. Alright, anyway, let's get into it. Number 1, or should I say A, Aufbau Principle. What is the Aufbau Principle? The Aufbau Principle is an organization method for electron configuration. It states that electrons will always fill the lowest energy levels before moving on to higher energy levels. Using this principle, we can create an Aufbau diagram to represent the distribution of electrons for certain elements. There are 4 orbitals, s, p, d, and f, from lowest to highest amount of energy. Each of these orbitals can hold a specific number of electrons. The s orbital can hold 2, the p can hold 6, the d can hold 10, and the f orbital can hold 14 electrons. An example of the Aufbau principle is the element of potassium, or K, has 19 electrons. If we were to use an Aufbau diagram to represent the electrons of this element, it would look like 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. B. Barometric pressure. What is barometric pressure? Barometric pressure is the pressure within the Earth's atmosphere. It is measured in atmospheres, or ATM. An atmosphere is the air pressure at the elevation of sea level and a temperature of 59 degrees Fahrenheit, or 15 degrees Celsius. An example of barometric pressure is, as elevation increases, the air pressure decreases. Furthermore, further up, the air molecules grow further apart and the density is immensely lowered. That is why, when you're ascending a mountain, it gets harder to breathe. Usually, in regular environments, the air is being pushed into your chest. However, at high elevations like this mountain, you must inhale air completely on your own. C. Chromatography. Chromatography is a technique to separate a mixture. It takes apart the mixture by allowing the natural tendency for components to rise to the surface of the material. As the components separate, scientists can analyze the different substances in a mixture and any product that was created from a specific reaction. An example of chromatography is that it's present in our everyday lives. It's used to create effective vaccines and even used by governmental agencies to find and track criminals using blood and DNA samples. With chromatography, the separation of components allows many jobs to be more efficient and function better. D. Dot diagram, also known as Lewis structures. A Lewis structure, commonly referred to by the name dot diagram, gives a visual representation of the amount and arrangement of valence electrons inside a molecule. To be stable, one molecule must have 8 valence electrons. When 2 atoms bond, their bond is represented by a line made up of 2 electrons on the dot diagram. The dots around the molecule represent the number of valence electrons there are. An example is dot diagrams are mainly present in organic and biochemistry. They help make it easier for scientists to recognize the amount of valence electrons in a molecule and the structures that connect multiple atoms together. E. Enthalpy. Enthalpy quantifies heat flow into or out of a reaction using the equation H equals E plus PV. H, or enthalpy, equals E, energy, composed of heat and work, plus PV, pressure times volume. Heat and work are pathway dependent, meaning that the type of situation scenario affects how much energy is produced. An example of enthalpy is a hand warmer. While under a constant pressure, the iron inside the hand warmer is exposed to the air, causing it to heat up. Using the heat and work used for energy and the constant pressure, we can calculate the enthalpy released by the hand warmer. F. Filtration. Filtration is a technique to separate a solid from a liquid. A filter paper collects the bigger solid particles, while the smaller liquid particles are allowed to pass through. The liquid that gets through the filter paper collects at the bottom of the glass, while the solid particles stay on top of the filter paper. Example. There are many different examples of filters in our daily lives. Coffee filters separate the coffee grounds from the water, preventing solid chunks from forming inside the coffee. Pool filters separate dirt and bacteria from clean water so people can swim safely. Greenhouse gas. G. Greenhouse gases are gases that trap and keep heat in our atmosphere. The sun emits radiation onto the Earth's surface. However, greenhouse gases keep this radiation inside the atmosphere. The buildup of radiation leads to a gradual heat rise over time, also known as global warming. An example of greenhouse gas is that a majority of greenhouse gases are composed out of carbon dioxide. This substance is mainly formed in large quantities through the burning of fossil fuels such as coal. Because of greenhouse gases, the Earth's temperature continues to rise, harming wildlife and melting large portions of vast glaciers. As you can see here, this contrasts the glacier percentage or mass of the glacier from 1909 to 2004. As you can see, it's not even present there anymore. Hess's law, H. Germain Henry Hess was a famous thermochemist who created one of the bedrock principles for thermochemistry, later becoming known as Hess's law. Hess's law states that the change in enthalpy in a reaction is found by subtracting the change in enthalpy for the reactants from the change in enthalpy for the products. The equation for Hess's law is represented by this. Hess's law serves various purposes in thermochemistry. Breaking down a reaction into multiple steps helps thermochemists identify when enthalpy was changed. It also helps find the total heat given by a reaction and provides a firm number to rely on when making calculations. Independent variable. An independent variable is a component in an experiment or reaction that can be changed by scientists. Unlike a dependent variable, it is unaffected by the other processes going on in the trial. These types of variables are essential to the most scientific experiments as they help the scientists search for specific results from different stimuli. An example is, independent variables are prevalent in chemistry experiments. For example, if I wanted to test how acidic different liquids are, I would test multiple liquids. Because I test out multiple different liquids to get a different pH level for each, the different types of liquids would be independent variable, and the pH level would be the dependent variable. Joule. A joule is a measurement for heat and work. It is one of the most commonly used units in thermochemistry. The formula for joule is represented by joule energy equals kilogram mass times distance divided by time. One prime example of the importance of joule is on the heating curve. For water, the heat of vaporization is 2,330 joules over grams, and the heat of fusion is 334 joules over grams. Knowing the mass of the substance, scientists can cancel out the gram symbol and find out the total heat in the reaction in joules, and if they divide by 1,000, kilojoules. Kinetic molecular theory, K. The kinetic molecular theory, or KMT, explains the behaviors of mainly gas molecules in chemistry. There are 5 different types of assumptions that solidify the theory, stated on this slide. These assumptions help chemists make more specific and accurate approaches to measurements, calculations, and different types of experiments. So here are the 5 assumptions. Number 1, all matter is made up of molecules or atoms. Number 2, all molecules are in constant motion. Number 3, collisions between molecules are elastic. Number 4, molecules are neither attracted nor repelled. Number 5, the average speed of the molecules, or kinetic energy, is related to the temperature, Kelvin, of the material. No temperature scale exists that actually measures Kelvin, but chemists use the equation Kelvin equals Celsius plus 273 to find out what Kelvin it is. An example of KMT is that it can also be applied to the real world. For the 4th assumption, for example, it would be disastrous if molecules attracted or repelled each other. Proof that this type of attraction doesn't affect us is the fact that we aren't instantly magnetized or repelled to whatever we go near to, because every substance has atoms or molecules according to the first assumption. L. Law of conservation of mass. The law of conservation of mass is a key aspect to any experiment in the scientific field in general. This law states that in any physical or chemical change, mass is conserved. Mass can neither be created nor destroyed during any reaction. Example. One simplistic and well-known example of the law of conservation of mass is a melting ice cube. When an ice cube melts into the water will still have the same weight as the original ice cube. For example, if a frozen ice cube had a mass of 5 grams, the water collected after the ice cube melts will also have a total of 5 grams. The mole. A mole is a scientific measurement used to quantify a large amount of small particles, such as atoms. 1 mole equals 6.022 times 10 to the 23 atoms. This is also known as Avogadro's number. Using these calculations, scientists can accurately identify how many moles of particles are present in a substance. So here's the example. Amedeo Avogadro revolutionized the measurement of tiny particles with the mole. He measured 12 grams of carbon-12 and listed the amount of atoms inside, 6.022 as 10 to the 23, as the new molar constant. Carbon-12 is still used today as a reference, as the average number of moles in carbon-12 is indeed still Avogadro's number. Neutralization reaction. A neutralization reaction is started when a strong acid and strong base are mixed. Once combined, it forms a compound composed of water and salt. This compound is neutral and doesn't hold any additional hydrogens. The amount of hydrogens in dissociation determine how acidic and strong a substance is in most cases. An example of a neutralization reaction is reacting hydrochloric acid, which is acid, with sodium hydroxide, which is a base. The base and the acid react to form a neutral solution. To prove that a neutralization reaction has occurred, it must have a pH of 7, which is a neutral pH. It must have products of water and salt. Orbital. An orbital is a region of space in an atom where there is a 90% probability of finding an electron. The closer to the nucleus, the greater chance of finding electrons. There are 4 types of orbitals, commonly known as S, P, D, and F. Each orbital contains a maximum of 2 electrons, each with an opposite spin. There are many different shapes that orbitals take up. For example, the s orbital is spherically shaped, while the p orbital is hourglass shaped. The size of the atom has a direct correlation to the amount of orbitals it will have. For example, look at the Aufbau Principle slide I said earlier. The periodic table. The periodic table could be considered the constitution of chemistry. The periodic table contains multiple rows of boxes, each symbolizing a discovered element. Each element is separated into different categories based on properties such as alkalinity. In the periodic table, each elemental box contains a multitude of information. For example, my periodic table specifically, the top of the box contains the number of element it is, for example 1. The middle of the box has the full-length name of the element, hydrogen, with its shortened symbol above it, H. At the bottom of the box is the atomic mass number, 1.008. There is so much more that is available to use through the periodic table. I put my own periodic table to the right so you can see how much information I use from it. Quantum mechanical model. The quantum mechanical model, QMM, was introduced by Erwin Schrödinger in 1926. It is the most accurate/realistic model of an atom according to today's scientific standards. While the former Bohr model of the electron had electrons traveling around the nucleus in circular orbits, the QMM instead has electrons grouped into electron clouds or orbitals. Understanding the atom is a vital mission to the scientific field as they make up virtually everything. For example, using models such as QMM, chemists can predict where electrons are going to be found. This data will allow them to better conduct experiments involving atomic structure. Reactants. Reactants are substances placed at the beginning of a reaction. They are mixed with a reagent to form a product. In a traditional reaction equation, reactants will be on the left-hand side of the arrow. Reactants are present in so many different reactions in chemistry. For example, this is what a chemical reaction would look like. Na plus Cl2 yields NaCl. The reactants in this equation are Na and Cl2. They are reacted to form NaCl. Standard temperature pressure. Standard temperature pressure, also known as SDP, is a set of conditions that allows for the most accurate data to be collected during an experiment. To break it down, standard temperature is 0 degrees Celsius, 32 degrees Fahrenheit, and or 273.15 Kelvin. Standard pressure is exactly 1 atm, or 1 atmosphere, 760 milligrams of mercury, or 760 torr. The combination of these conditions are SDP. Using SDP, chemists are better able to identify the properties of gases. Pressure of a gas is relative to how fast and how hard the gas molecules are hitting the edges of the holding container. Absolute temperature is measured as the amount of kinetic energy being exerted by the gas molecules. So chemists can use this in a variety of ways for multiple experiments. Theoretical mass. Theoretical mass, commonly referred to as theoretical yield, gives insight into how much of a product is formed using stoichiometry on paper. According to stoichiometric rules, the maximum amount of a product that can be formed is the same amount as the product of the limiting reactant. This limiting reactant, calculated by the equation, is known as the new theoretical yield. Theoretical yield contrasts with experimental yield, as theoretical yield finds mass using stoichiometry equations on paper, while experimental yield is based on actual experiments conducted in a lab, thus being more accurate. An example of theoretical mass is using the equation Fe, or iron, plus S, sulfur, equals ferrous sulfide. The limiting reactant is iron and has a mass of 12.0 grams. This becomes the theoretical yield as well. We also would be able to find the experimental yield by using real-life experimental data. The experimental yield for this reaction is 10.6 grams. And we'll see it later on as I reference this in another slide. Universal indicator. A universal indicator is a test to determine the pH of a substance. Colors are used ranging from red to purple based on the acidity of a substance. Substances with an acidic pH of around 1 have a red color. Substances with a neutral pH of 7 have a green color. And basic substances with a pH of around 14 have a purple color. When testing the pH of pure water, the universal indicator would appear green because of the neutral pH of 7. For example, orange juice has a pH of 3.3, making it moderately acidic and around an orange color. If testing milk and magnesia, the pH would be at 10.5 and around a blue color. V. Valence electrons. Valence electrons are particles on the outermost shell of the atom. These valence electrons allow atoms to bond with one another during chemical reactions. In most cases, they also determine the reactivity of the atom. For example, a simple trick to finding the amount of valence electrons an element has is looking at the group number or column number of a periodic table. The S and P blocks of the periodic table contain the elements that have valence electrons. For example, if I took hydrogen, which is in this S block, it is in group 1, meaning it has one valence electron. Wavelength. A wavelength is used to measure the frequency of a wave, specifically finding the distance between two wave crests. The dip between the two wave crests of the wave is called a trough. Wavelength is represented in equations and formulas by this symbol. Finding wavelength is very helpful as it helps to determine the frequency and power of waves being emitted. Shorter wavelengths have higher frequency and energy, while longer wavelengths have shorter frequency and energy. Gamma waves, being the most powerful, have very short wavelengths, while weak radio waves have much longer wavelengths. Waves are emitted from multiple devices, for example, ranging from microwaves all the way to space satellites. X-ray. An X-ray is a machine that uses electromagnetic radiation to photograph the internal structures of the body. Because some parts of the body absorb the energy more than others, doctors are better able to search for specific biological structures. The parts of the body that absorb more energy have a faint luminescent glow that contrasts with the dark background of parts that don't absorb as much. When using an X-ray machine, doctors usually look for fractured bones. However, they might also look for damaged tissues or organs. For example, chest X-ray scans can detect pneumonia and the possibility for breast cancer. Because of the high intensity of X-ray waves, some medical centers offer aprons to protect certain parts of the body, as you can see right here. Yield, the last one. Yield is known as the products of a reaction. A type of yield, known as percent yield, specifically, is one of the key aspects measured when chemists contrast experiments. Percent yield measures how accurate the results of an on-paper stoichiometric calculation, or theoretical yield, is, compared to the results of a real-life experiment, experimental yield. To find the percent yield, we would have to divide the experimental yield by the theoretical yield and multiply it by 100. Again, referencing the previous problem, Fe plus S equals FES, the theoretical yield calculated on paper is 12.0 grams. The experimental yield for this reaction is 10.6. Once dividing the experimental yield of the theoretical yield and multiplying it by 100, we get the equation 10.6 divided by 12 times 100 equals 88%. The answer shows that the real-life experiments only produced 88% of the predicted yield using theoretical yield calculations on paper. And I skipped Z. And that is it. Thanks for looking at my chemistry A to Z final project presentation. I hope you enjoyed. I put a lot of work into this. So yeah, I'll see you later.